continue with our discussion on fin heat transfer. In the last class we derived the fin equation and we also saw solutions, analytical solution to the one dimensional fin for constant area, constant cross sectional area. I told you that if you have variable cross sectional area it will lead to Bessel function, right, and there are another type of functions like your trigonometric functions or hyperbolic functions and so on, but it is a lot more involved. But nowadays all these fin problems can also be easily solved using MATLAB and other things. I mean or your COMSOL or star CD and Fluent and so on, right. But we are looking at analytical solutions basically because they are elegant and you can get a quick back of the envelope calculations, how many number of fins are required and all this. So for fine tuning the results you can use sophisticated software, right. If you look at the right, we derived this temperature distribution in the last class, right. So correct. So this is the expansion for cos HML, cos HML minus x in the numerator and cos HML in the denominator. So when the fin is very long, right, if you have a case of a fin where the length is very large, then we will have, okay, for the case of a very long fin ML is much greater than 1, therefore is that okay. So we will call this as long fin. So what we are doing is to derive the expression for the temperature distribution as well as for the fin efficiency for the long fin, we just first consider it to be an adiabatic fin tip and start working on it. Now it is okay for me, so I will say this is 1, 2, what happens when ml is much greater than 1, what happens to e to the power of minus 2 ml, huh? Okay, when ml theta b by theta b e to the power of minus mx, it turns out to be a very simple case of exponential distribution, okay. Even otherwise the temperature distribution is exponential, but it has become very simple. Okay. Now but we will have to answer the question how long is long. we will try to answer that question, right. Now we can work out the agreed. So e to the power of minus mx, derivative is m minus m e to the power of minus mx, substitute x equal to 0. So this minus and minus will get cancelled, so we will get plus. K is the units of watts per meter per Kelvin, A is meter square and m is 1 per meter, correct. So there is a 1 per meter in K, there is a 1 per meter in m, there is a meter square in A, so the meter square get cancelled, so the whole expression is in watts, correct. Okay, now what is the Q max? The maximum heat transfer possible. The maximum heat transfer which is possible from the fin happens when the whole fin is at the base temperature, that is T equal to Tb throughout or theta equal to theta b throughout. Please remember theta is the temperature excess, T minus T infinity, right. So this will be HPL therefore what is this 1 by m square. As expected, the efficiency of the fin will decrease as the length of the fin increases because eta is 1 by ml, right. We should not use long fins, long fin itself is an approximation, but we should use less number of short fins instead of small number of long fins, because towards the end the temperature difference will be, the temperature difference with respect to the ambient will become lower and lower consequent upon the temperature distribution being like this. So if you divide the fin into 3 parts, if you take a 10 centimeter long fin, divide into 3 parts, 3.3, 3.3, 3.3 centimeters, the first 3.3 centimeters will give terrific heat transfer rate because theta is very high. The second 3.3 will give okay, the last 3.3 will give very poor heat transfer rate. So if you keep on increasing the fin length, the last portions of the fin are totally useless because they will be at only a few degrees above the ambient temperature, no point. Instead you can cut them down and crowd the base with more fins. Of course that may locally affect the heat transfer coefficient, but you can put some fan, something, increase the velocity and do something. That is what I showed you the heat sink, right, with a fan and very closely packed fins, alright. Now how long is long? That question has to be answered. Yeah, can you tell me when ml equal to 5? 0.9999, right? The first step in technology is to calculate the m of the fin, multiply it by L, get ml. If ml is 5 or above, straight away use the long fin relation. There is no need to worry whether it will be adiabatic fin tip. It is so long that the tip of the fin will be just a few degrees above the ambient, and the tip area is also less. The area is less, the theta is also less. Why would it lose so much of heat? Okay. Okay, let us solve a problem. Problem number 44. Problem number 44. A long circular aluminum rod. Problem number 44. A long circular aluminum rod, K equal to 205 watt per meter per Kelvin. A long circular aluminum rod, K equal to 205 watt per meter per Kelvin, is attached at one end. To a heated wall. Long circular aluminum rod, K equal to 205 watt per meter per Kelvin, is attached at one end to a heated wall, full stop. The fin transfers heat by convection. The fin transfers heat by convection to a fluid, full stop. The fin transfers heat by convection to a fluid, to a cold fluid, full stop. A. If the diameter of the rod is tripled, if the diameter of the rod is tripled, how much will the heat transfer rate change? If the diameter of the rod is tripled, how much will the heat transfer rate change? Question mark. B. If a copper rod is used, within brackets K equal to 390 watt per meter per Kelvin. If a copper rod, bracket K equal to 390 watt per meter per Kelvin, close bracket, is used instead of aluminium. If a copper rod is used in the place of aluminium, by how much will the heat transfer rate change? By how much will the heat transfer rate change? This is a simple problem which gives you a practical aspect of what is the effect of a change in the geometry on the heat transfer performance of a fin, part A. Part B, what is the change in the material used in fins? Okay. I have already told you you have to look out for the buzzwords. A long copper rod, a long aluminum rod means it is a long fin, okay, and it is attached to the base. You do not have to write the governing energy equation for conduction in cylindrical coordinate, try to solve and all that. It is a simple problem. At this point I would like to caution you, when we solve the one dimensional problems, I do not know how, I expected this question from somebody. When we solve this fin equation, we already spent one full hour trying to take a control volume, identifying what is the energy term inside this thing, moving velocity and all that, and got the energy equation. And then we started looking at slab without conduction, without heat generation, with heat generation, and we applied boundary conditions and solved the problems. Why did we have to derive the governing equation separately for a fin? Why can't we use the governing equation which we derived, the generic governing equation? Nobody asked this question. Yeah, there the problem is what we are doing is you can still solve the Fin equation using the concept of using the general energy equation, but you have to say that T is a function of x and y and then apply the boundary condition separately on each of the walls. But here we took minus k dt by dx is entering, minus k dt by is leaving, and then in the other direction we are just lumping it by a convective heat transfer process. Directly we are supplying the rate. Therefore, by energy balance, which used to come as boundary condition, at the boundary convection is equal to conduction, that is now integrated because we are lumping. If on the other hand, if you want to use T is if you want to solve the Fin problem as T is a function of x and y, then go ahead and use the original governing equation. Are you getting the point? So the general governing equation cannot be used to solve the one dimensional Fin equation, to derive the one dimensional Fin equation. We have to do it separately because we are lumping the heat transfer across the y direction, because we are saying that the thickness is so small that there is no temperature distribution in this. If there is no temperature distribution in this, but there is a convection which is taking place, how to factor in this? HP dx into theta, we put it into the equation. Is it okay? All right. So correct. The first case we are changing only the m, right? Okay, q1 is k right. So there is a mnemonic here. Q is root of h pack theta b, so you can remember like that, right? Q is equal to root of h pack theta b. I would, okay. Okay, now Q2 okay, therefore correct. So the diameter is doubled, or tripled. Huh? 5 point? Okay. Very impressive. But suppose we are trying to do something like this, okay, in a satellite which is placed in the PSLV. We want to do some heat sink design and all that. Vamsi, what happened? Is it not clear? The heat transfer rate has increased by 5 times, very good, but the weight has increased by 9 times. So if you have hundreds of fins, it is not commensurate with the, so just because it is 5, it is very good, the things have, the fins have become thicker and they may have become heavy, okay. So there is a penalty associated every time you try to do something, then there is some other penalty, okay. Now part B. So the weight has increased 9 times because the diameter has tripled, okay. So it will go as diameter square, weight will be 3 into 3, 9 times, okay. Huh?
Number of fins also will be decreasing. Base area will be remaining constant.
No, that is only if you want the Q to be constant. What I am saying is, suppose you want to increase the Q itself. What I am saying is, if you want to increase the Q itself, I am saying that this, just because you tripled this 5.2 times is not coming for free. That is the point I want to emphasize, okay. B is right, all other things are the same. How much is it? 1.4. Again, what is the density of copper? 8,900 kilogram per meter cube. What is the density of aluminium? 2,700. So if you replace aluminium by copper, there are several dangers. Weight is increased, okay. So copper is very expensive. Now you can see this sort of exercise gives you an idea of the basic heat transfer processes, how each of these parameters influences the heat transfer rate. So this gives you a good idea of the role of various parameters. I can also use this, I can also conduct some experiments where I have long fin, I measure the temperature at 2 places, okay. Then I know that theta by theta b is e to the power of minus mx. Now I can solve it as an inverse problem and get the value of m. From the value of m I can get the value of thermal conductivity, right. So you can do some additional, I don't normally I do a problem like this, I do not have time now. That is, you have a fin, set up and measure some temperatures, then you keep on guessing the value of thermal conductivity, it will give a theta minus, it will give a theta versus x like this for various values of k. There will be only one value of k which gives a curve which is closest to the experiment, and that curve should be the best representation of the thermal conductivity. So that is a basically what is called an inverse problem, okay. Now we will go to so we have to look at the energy equation in cylindrical and spherical coordinates. I do not have time to derive that, but they can be derived in a manner analogous to how it was derived for the Cartesian coordinates, right. So So if you have something like this, this sort of geometry occurs basically in double pipe heat exchangers, that is concentric tube heat exchangers, nuclear fuel rods, they are mostly like this, okay. So the temperature could be a function of the radius r, correct. The temperature can change along the axial line, axial distance z, then there is this coordinate. So this we call theta, this angle. So T of r It is called an r theta z coordinate, theta r z. Mostly unless you have a very an circumferentially varying heat flux, theta will not be a function of, or T will not be a function of this angle theta, unless you have a special heat flux, sinusoidally varying heat flux or some non-uniform heat flux. Generally it will be uniform along the azimuth, but temperature will vary, usually across the radius it will vary, and oftentimes it will vary with z also. So the governing equation for this will be rho Cp okay. This is for a uniform thermal conductivity K, right. So please note the essential differences between this equation and the Cartesian coordinate equation. Have you written this down? The essential differences are, the left hand side is the same, the right hand side you have got 1 by r dou by dou r of r dt by dr. We used to get d square t by dx squared there, but why is it 1 by r is coming is basically, if you take a section r, if you take a section r plus dr, there we put minus small q at x is equal to minus small q at x plus dx. Here you can't put that, it will come, you have to put minus capital QR equal to, because capital QR is small qr into 2 pi r dr, 2 pi r plus dr. So that is why the dou by dou r of r dt by dr is coming, the area continuously changes. It is not a constant heat flux across the radius, constant heat, there may be constant heat transfer rate, but heat flux is not constant. Then theta is dimensionless, therefore d squared theta by d theta square has to be multiplied by 1 by r squared, otherwise it is not dimensionally consistent, then d squared t by dz squared, okay. Now for the spherical coordinates, we saw the spherical coordinates in our discussion on radiation, okay. So there is r, okay. So instead of 1 by r, what do you expect for spherical coordinate? 1 by r squared plus 1 by r squared sin theta. So I have asked the derivation of this equation as a question in the end semester examination, say 8-10 years back and all that. Don't worry, nowadays I don't do such thing. Can be derived, but it's very painful. Take a long time. If it is just a conduction course, we can do it. Okay. Now, please keep this. Suppose in the exam I ask you questions on simplified forms of this, you start from this equation, and if it is unsteady, remove the left hand side, no QV, remove the QV term on the right hand side. If it is only one dimensional, remove the functional variation with respect to here in this case theta and z and proceed. Okay. Let us get some analytical solutions for simple cases. So let us consider a double pipe heat exchanger. We are not worried about temperature as a function of z or theta, temperature is a function of r only. So I have a solid material here, so it is an annulus, the temperature here is T1 at R1, this is R2, it is T2. This why it is T1 and T2 is basically because some fluids may be changing phase. The correct description would be to give a heat transfer H1 and T infinity 1 and H2 and T infinity 2, but if I give you that it becomes very messy, but we will incorporate that into our analysis by using our resistance concept. But first we will solve the simplified form of the governing equation. Is the situation clear? So it is 1D steady QE equal to 0, T is a function of R only. Okay, there is a pipe which is like this. I am taking the sectional view, it is a sectional view of the pipe. So this is the thickness of the pipe material or tube material. Okay. Now please reduce the governing equation will be so governing equation is from this dou by dou r of r dt by dr equal to 0, that is it. I can make it d also, no need for dou. Is everybody through with this? The left side unsteady term is 0, right side d square theta by d theta square 0, d square t by d z square 0, qv equal to 0. Because everything else is 0, dou by dou r can be changed d into d by dr. Now integrating once, okay. Now integrating again, T equal to A ln r plus b, correct? To substitute the two boundary conditions at r equal to r1, t equal to t1, at r equal to r2, t equal to t2, that is specified to us. Subtracting 6 from 5, the b will get cancelled, you can straight away evaluate a, right. Is that okay? Ln of r1 minus ln of r2 is ln of r1 by r2, right. Is it correct? Nirban, is it correct? Okay. Therefore, yeah, it is easy to see. At r is equal to r1, what is ln of r by r1? At r, where? Ah, okay. At r equal to r1, this becomes ln of 1, it is 0, so t equal to t1. At r is equal to r2, this will become r2 by r1, this will be minus 1, so t1 minus t1 plus t2. So the equation is correct. So we check it for asymptotic correctness. Okay. So we got the temperature distribution. We are interested in the heat transfer rate. This has to be correct. That's how we wrote the equation d by dr of r dt by dr equal to 0. Okay. So if this is the case, what is dt by dr? A by r. A by r. Okay, dt by dr at r1 is a by r1. A by r1. What is a? T1 minus t2. That's it. By r1. I can take care of the minus sign by writing the denominator as ln of r2 by r1. Okay. Okay, when I say q equal to delta T by something, what is that the delta T by something? That is the resistance. What is the only resistance which is occurring in this problem? It is the conduction resistance because of finite conduction across the thickness of the tube. That resistance will vanish in the event of the thermal conductivity of the material tending to infinity. Okay. So this is therefore the conduction resistance involves a log of the ratio of the radii. So the natural log occurs naturally in the case of conduction in cylindrical coordinates. This did not come in the case of conduction in Cartesian coordinates. It is basically the only source, the only culprit for this is the changing area 2 pi r dr that led to A by r, which led to A ln r, okay, which may also lead to problems when you are solving for conduction within a solid, then what will happen to the temperature at the center? So you have to take care of the boundary condition at the center. Okay. You may say dt by dr is 0 at the center if it is a solid cylinder. Dt by dr does not mean it is insulated. Sometimes what we do is at the center we apply what is called the finiteness of temperature condition. The temperature has to be finite. Okay. If time permits, we will solve a problem where we take a solid cylinder. Okay. Now this pretty straightforward. Now we will go to the actual case. What is the actual case? H1 T infinity 1 R1 R2 H2 T infinity 2. So I do not know the boundary I do not know the temperatures T1 and T2 at R1 and R2 respectively. Rather I know the temperature of the fluids which are flowing on the inside and the outside and the heat transfer coefficients. This is possible in a double pipe heat exchanger where cold fluid is flowing inside and hot fluid is flowing outside. You are trying to accomplish heat transfer between the two fluids. Why can't you mix the fluids? I may ask. We do not want to do that. Okay. One could be oil, one could be sodium. Okay. It happens, right, in a sodium to water heat exchanger or something. Okay. Now what is the heat transfer rate? What is the L? I am keeping on talking about some L. L is the length in the direction perpendicular to the plane of the boat, right. So yes, okay. So now we use the dividendo componendo rule and say it is the same Q which is coming outside, from inside to outside is the same Q. Therefore using the dividendo componendo rule we can add the numerators and denominators separately, still the resulting expression will be equal to the Q which is occurring across the tube. Therefore so the three terms in the denominator are, the first term represents the convective resistance on the inside, the second term represents the conduction resistance across the thickness of the tube, and the third term represents the convection resistance on the outside. The first and third terms are also called as the the first and third terms are also called surface resistances. Okay, so using the concept of electrical analogy. We can say so you have the potential difference T infinity 1 to T infinity 2 . In the event of H1 equal to H2 equal to infinity, it will reduce a simple expression which we derived some few minutes ago. Now we can have a composite wall where apart from the inside and outside surface resistances, we can pack this with insulation. Therefore, you can have terms like ln of R2 by R1 2 pi Ka into L plus ln of R3 by R2 into 2 pi Kb into L. Okay. That is, you have got, suppose you are looking at an insulation design, you are using 2-3 types of insulation. There is a metallic wall, then you put glass wool, then you put something in. What is the idea behind this? In all these industrial establishments, when you are carrying hot fluid, the outside temperature cannot exceed 65 degrees because that is the temperature at which people will get hurt. Okay, so the outside temperature should not be more than 65 in all these open ends because somebody will go and touch it. So you will have to keep on insulating, and also you do not want the, by the time it leaves this boiler room and goes to the turbine room, you do not want it to get cooled, right. You want to exploit the full enthalpy of the steam. Okay, so when you come to insulation design, all these things will come. There is also a point of critical, you can also work out what is called the critical insulation thickness, okay, which you must have done in your undergraduate heat transfer course. So we can use the dividend component rule and arrive at results like this. In an exactly analogous fashion, you can derive basic relations, analytical solutions for one dimensional heat transfer across a spherical shell. Why is a spherical shell so important? Because you want to carry cryogenic fluids, you want to carry nuclear fuel waste and all that, and then if you want to put several layers, then there can be Ka, Kb, Kc, right. So if you are not able to solve, we can solve problems in the exam also, okay, in the class, right. So there are a lot of opportunities for me to ask questions on conduction in the exam. Now we will stop here.